Okay, so here's a problem that involves, again, finding the internal value, internal forces at a point. I think it says C. So if I again make a much more stronger line at C, and I want to look at the left side or the right side. Now, like some of our previous problems, you can see that the reactions don't pose a big difference. I'll have a vertical reaction at A. I'll have a vertical reaction at B. Okay, but now look at the shape of the distributed load on the left side compared to the right side. The left side is a triangle, and the right side is a trapezoid. And trapezoids are a little more challenging to work with. Even if you break it up, you're going to have a triangle and a rectangle. So I think you'd have less work if you did the left-hand side. So let's use that as our strategy. So I'm going to really be focused on the reactions at A. So let's go ahead and assume that I have a Y component and an X component. Now when I'm summing moments to find this, I'm going to sum moments about B. So first thing I want to do is take this distributed force, and resolve it to a concentrated equivalent. Now all I have to do is find the area under the curve. And fortunately for us, that's a triangle, and most of you remember an area of a triangle is 1/2 base times height. So it'll be 1/2 the base, which is 18, times the height, 3. I believe that's 27. Now, where's the centroid of a triangle?
1/3 away.
1/3 from the big end, right? So there's my 27 kip force. I'm also summing moments about B, so the distance from B to that will be 1/3. 1/3 of 18 is 6 feet. So now when I'm summing moments about B, my 27 kip force creates positive or negative moment about B? I'm using right-hand rule, so it's positive. So I have 27 kips times 6 feet for my moment arm. And then the only other force is the reaction at A, which creates negative moment at 18. So it looks like AY is going to be 9. And just to be complete, if I sum forces in the x direction, make sure I have the equilibrium, all I have is AX. So AX is 0. So I found all my components there. Okay? So now I'm going to actually make the cut and look at this free body diagram. I'll draw it a little bit larger so we'll have some room to work with. So again, that's 6 feet, so I'll say that's 6 feet. And then I'll have the triangular loading. I'll have my reaction at A, which I've solved for. That's acting up 9 kips. My internal forces. So I'll assume positive shear force, positive axial force, and positive bending moment. Now, one little extra thing I don't know is what's the intensity of the load here at this cut?
So you just do the similar triangle.
Yeah, you can do similar triangle. So I know that at 18 feet, it's 3. So at 6 feet, it should be, it's 1/3 the distance. It should be 1/3 the intensity. So that value right there is 1 kip per foot. So this will be 1 kip per foot. So with that information, I can now find the concentrated equivalent force of this load. Just like up here, it's a triangle, so 1/2 base times height will give me a value of, what, 3? 3. And the distance is 1/3 from the cut, and that will be 2 feet. So there's my free body diagram. Again, if you're doing this on the exam and you get this, you're at this point, you're 2/3 of the way there for me, maybe more. This would almost be passing that problem if you just got to this point. I consider the rest to be pretty much just plug and chug. So you're just going to sum moments about the cut. Right hand rule is my sign convention. So this moment, internal moment MC, is positive. My 3-kip concentrated force with the 2-foot moment is positive. And then the reaction of 9 kips is negative moment. So that's 9 kips times a moment arm of 6 feet. So it looks like the moment at C is equal to, it's positive, what is it? 45?
8. 9 times 6 is 54, minus 6.
48?
Yeah.
You guys just doing that off the top of your head? It kind of scares me when you do that.
Well,
But it is 48.
Negative 54 plus 6 is negative 48.
I believe you. Came out positive. Does it make sense that this structure has positive bending moment at C?
Yes, sir.
I think so. How's it going to bend? Is it going to bend up? Or is it going to bend down? Down. So this is not the correct shape, but you can see that it bends into kind of a big smile, so it's positive curvature, so you'd expect positive bending moment. And just to finish this one up, shouldn't be much trouble to go ahead and sum forces in the vertical direction. I'm assuming up is positive, so this VC force is down, shear at C. The 3-kip force is down. 9-kip force is up. So it looks like the shear at C is equal to 6 kips. And then just to complete the whole setup, if I do sum forces in the X direction, make sure it's in equilibrium. The only X component I have is the axial component, and it seems there is no axial force. And that's that. Any questions about that?
So even though this gets larger as you go across, it will be the same on both sides since it's distributed load?
I'm not sure exactly what you're asking, but if I were to cut and look at the left-hand side of this body, if I had worked this structure, right, with the reaction at B and this distributed load, I would get the exact same results.
That's what I was asking, though it gets different since it's distributed load is the same.
It would probably be very distracting and disturbing if you worked one side and got an answer and worked the other side and got a different answer and they were correct. So it's the value of moment at a point doesn't really jump. Now, as you move from a concentrated moment from left to right, it will jump, just like the shear will jump when you go under a distributed load. But for continuous loading like that, you won't see those jumps.